Hello, welcome back. I'm back with a new tutorial video for you on Rhino Grasshopper tools. So in this exercise file, we're going to look at a spiraling ramp and a digrid formation around it. But the interesting aspect of this tutorial is going to be this type of connectivity of the structure with the ramp. So this was kind of a low resolution screen capture that I had where I baked a bunch of variations. But we will be generating this form of the ramp using graph mappers, and then we're actually going to connect these points using curves and manipulating the point lists basically. And you can actually control the number of divisions, points, as well as the spirals in this exercise file. So we're going to build it from scratch. If you're interested in this type of content, please consider subscribing to the channel to support it. I'm trying to get to 10,000 subscribers, so the channel has been growing with your support, but I would like to be able to contribute more to this channel. So if you can hit the subscribe button and like this content, it will help immensely to support the channel. So thank you in advance. So let's begin by actually generating the spirals. So we are first going to do kind of a radial geometry or point cloud distribution that we can connect in the spiral form. So let's actually think about how we develop this first. So what I'm going to do is actually first thing is we want to generate a cloud of points. So when we construct point, consider if this were to be a circle, right? So since we are going to do in 3D, this is going to be kind of a helical motion. So I want to basically generate a bunch of points around pi, and we want to be able to basically assign this to a sine and cosine function. So basically consider that we want to, for instance, divide 360 degrees, and we want to divide it into, let's say, use range. We want to divide it up into 12 points, right? So each point would basically get a 30-point angle. Now, these could be actually converted to sine and cosine functions, where we use it to kind of draw the circle. So if I were to basically assign a sine function here for the x value, and a cosine function for the y value. These are in degrees at the moment. We don't have a radians version, but when we connect them, you actually get the points. But I think that this has to be cosine, this has to be sine. And let's look at this. I think it still reads them as radians, so it's kind of turning. They're not equally distributed around these angles, so we want it to be from 0, 30, 60, and we want it to continue. Let's see, this seems like this is kind of a different point, so probably we have to convert this to radians. So let's do that and see what we get. There we go. So when we multiply these degrees with radians, what we find is that these points, we're basically dividing 360 degrees into increments, and we are multiplying cosine and sine functions to draw a circle, right? So if I were to basically interpolate between these points, this will become just a circle, right? So what I want to do instead is to extend these points in 3 dimensions. So I want to add a z component to this, and I also want to add more turns to this function. So basically, let's assume that we are turning 360 degrees every way, and I want to multiply the amount of turns. So we can directly multiply the amount of turns. Let's say we want 12 turns, and so this will be a total of 4,320 degrees in motion, and we want to make it in some amount. Let's actually divide this number, so we could do division. So I want to divide this total angle into increments of 30 degrees, right? So that will give me 144 steps of division. Now we can actually do this in a bunch of ways. So I can control it by turn count. So if I want to go bit counts of 360-degree turns, then I can control how many turns I want, right? So this will be number of turns. Let's actually write it here. Number, we cannot do hashtag, unfortunately. So num turns, and this is the turn degree, turn angle. All right, and this will be the amount of steps, but in fact, the amount of total steps is right here. So what I want to do now is define the total turn, 4,320, and turn this into 144 steps. So now you can see we have actually overlapping points because we are incrementing. Now we get actually a lot of points. We get 145 points, but they're overlapping. So all I want to add one more thing to this is the Z. Basically, I want to extend the increment. Now, how can we do that actually? Let's think about it. So we have points, and these are the angles. So how many points do we get? We get 144 points. So we can do this in a bunch of ways. Imagine that we want to get to a level. Let's say we want to get to 30 meters in 12 turns, right? So I can actually divide 30 as my total height into 144 steps. So I can create another range here, supply 30, and divide it into 444. So these will be the incremental steps. Now if I supply Z to this, we can actually get a spiral forming immediately. So this is actually going to the height of 30, and it is having a unit measurement of 1 at the moment. So we are not overriding the radius of this. Now to override the radius is actually pretty straightforward. So if I multiply the x and y coefficients with some value as my radius value, let's say that radius is 6 meters, I can actually calculate a radius that is larger, right? So that will be a spiraling ramp that has a 6-meter radius. We can actually control lower radii as well. So in order to convert this into a ramp, we can actually make a secondary point cloud like this and supply another coefficient. Let's say we want to ramp width to be 1.5 meters. Then I can subtract from these values 1.5, and I can assign these x and y values to the other points. So let me see. We are splitting the radius value here. Is this correct? So I think it's also moving it around. So let me see. We probably have to multiply with a lower coefficient, so we cannot subtract it. What we can do is subtract this value as the stair width and then multiply it with these coefficients and then use this for the x and y. Yeah, so that's basically a shorter turn inside. But what's critical here is that when you look at it in the section, you can see that these points are actually on the same z level because we are supplying the same z, and we actually get two curves. So technically we can loft these now and we will get a spiraling ramp. And we are technically done with the complexity of the script. All I can do here now is we can control the width of the ramp. We can actually control the radius of the full ramp. We can also control the full height, right? So this is almost like an accordion. We can also control the amount of turns. For instance, I can do increments of 15 degrees. Now we will get more points. And we can also control the amount of turns. So I can actually go to this height in lower turns, right? So this is a fully parametric spiraling ramp model that we can use for multiple purposes. Now, one more thing I want to add to this is, what if we want this to have a more sculptural shape, right? So for this one, I'm actually going to use an input of a graph mapper. We can actually also use rich graph mapper. I covered another video on rich graph mapper. Let me see, rich graph mapper. So this one, what we could do is we don't have to supply the same multiplier for every level. So let's say that this 4 is basically changing throughout the levels. So I can actually override it by supplying a different multiplier for the full form. So basically 241 points we can actually get. Let's find out. So we can actually get another range here. And now the domain will be between 0 and 1. And we want to evaluate 240 increments. So these will be the values. So the source domain will be 0 and 1, and target domain will be 0 and 1 as well. So I'm just going to basically generate a random curve here. Let's say this is my curve, and I'm going to just add another multiplier here. So that let's multiply this with the full radius value 4. This will become a manipulator for the vertical amplitude of how much we want the spiraling points to move outwards. So I have to basically replace everywhere this 4 is connected now. So this, it will go here, and it will go to these points. And let's see where else. Does it go anywhere else? So let's see, why didn't this work? This is the point. Probably this is becoming too small, but let's see. So these are the two curves, which seem to me that they're actually correct. But let's delete this. And what we could do is look at the points. And the points seem actually fine. These curves are also okay. Maybe it didn't connect them the way we wanted to connect. We could also do it this way. For instance, we can create a line between these 2 points, and we can just loft these lines. So that would actually make this a lot better. So you can see, I mean, when I lofted these curves, the inner curve is actually shorter, so it's kind of creating a twist when we directly connect them. So this is the spiral that we are going to work with. So basically I can control the overall radii, and I can actually control how I want to manipulate the width and the height, right? So this is controlling the section of the spiral. And we still have these functions working. So I can control the width of the staircase. I can control the total height of the staircase, as well as the angle increment. So we can take turns in 30 degrees. We can also control how many turns we want. We can make it a lot or less, right? So the other second part is basically when we have, let's say, these points, I want to create a structure that connects through them. And that is actually done by combining these points that are at the end. We can also do an inner skeleton to this, but I'm actually going to group these points here. So what I want to do is we have 169 points based on this calculation, and I want to basically do a partition list here. So let's do a partition list, and I want the partition to be let's say controlled by how many points we have in one turn, right? So when we divide 360 by 15, we get kind of a value. So I can do another division here, but divide 360 degrees. So that's 24 points that we generate in one turn. So if I do a partition in 24 points, we basically get a data list that is like this. So there's actually 1 point left there, which is going to be an issue. So what we need to do is actually get rid of it. Maybe we can actually do after range, we don't we basically eliminate the last point, or we can also do a shift list, but technically we want to visit these points, right? So we can actually do let's do a shift list here. So I want to shift this list. Maybe we don't start with the same the first point. We don't want to wrap these values, and we want to have a total of 168. So when we divide it, now we get 6 lists, 7 lists, because we have 7 turns and 24 points in each turn. So if you do a flip matrix here, that will actually change the data to a horizontal version. So right now we have 7 lists with 24 points. We want to have 24 lists with 7 points in them. And this will become basically a vertical list. So if I interpolate these points now, you would actually get a vertical connectivity, something like this. So this would be basically a structure. And if I do a pipe, that was kind of what I had in the file, and 0.5, let's say, my radius. We can also make this a bit lower. So these are the tubes that are connecting. But I wanted to make it into a digrid. And one way of making it into a digrid is actually, after doing the flip, we can actually shift the ordering of the point lists inside of these groups. So basically, we can actually do a shift list function before we do the after we do the partition, I think. So let me look at the original file. I think that's what I had, but we actually do a partition of 22. Oh no, actually I do the partition, I override the partition. So we can do 2 partitions in this case. So let's look into that. So rather than doing a partition of 24, I can actually do a lower partition, because the reason is when we do partitions of 24, then it becomes a vertical connection. But if I do, let's say, partitions of 22, then I will be basically connecting to the upper points at an angle, right? So this point here, it will be connecting basically to an earlier list index. So if I do -2 ... 2, so let's do 24s, you can see that that's actually tilting the connectivity of the list. And if I make it into a 0, it will be vertical, but I can actually connect to an earlier group of points. And if I add a plus direction to the same partition, and let's see, this would be the new segmentation. That's it. Now we have actually the ramp and the geometry. So let me actually connect these all in the same list. So that's our parametric spiraling ramp with digrid. Now that might actually seem easier than done, but that's basically it. It's kind of a simple model, and we have a lot of control here. So basically we can control the amount of turns, how many turns we want to get to that height. Let's actually reduce this to be 20 so that we can have the lower connection, let's say 8. We can control the amount of points, so that will control also the density of the digrid, and we can actually lower this as well to add more points and turns. This also controls the full height of the model, right? So it could be short or long, and that's pretty much it. So this is also controlling the section. So I can generate another type of section. Maybe we want it to open up towards the bottom, and we want it to basically have any type of sculptural form. We can also control with other types of graphs, 5 or 6 points, if you want to have more control. So that's almost controlling the section of it, right? So it's almost working like a profile or a revolution. Right, so it's starting to look like a cup almost, but this is kind of the shape that kind of looks the best with this type of calculation tool. So that's pretty much it. And we can also bake some variation. Let me actually mold this into something a bit more smoother. So I'm going to make 4 points. And it's almost like a bottleneck. model, maybe something like this. And I'm going to bake everything here. That's it. So as I mentioned, the nice thing about this one is you can create a lot of variations, but you can see that the connection of the diagrid is at the ramp points, right? So that's kind of what we want. So we want the structure to follow the inner ramp as well. So that's why we are using the points. So that will be it for this tutorial. I hope you liked it. I want to mention my announcement again. Please consider subscribing to the channel if you're interested in learning these parametric tools. I'm also looking forward to uploading other content, maybe some AI content as well. This is kind of, I think, a fun way of learning about algorithms, developing relationships, and making it interactive parametric model as well. So I hope you liked it, and I'll see you guys in another video in the future. Take care.